Ryan Speers, Sophia D'Antoine, 20 devices in 45 seconds. Automate bug hunting and IoT devices. We cover program analysis for vulnerability discovery, demonstrating how to find new and previously known bugs across 20 IoT devices, and how tooling arguments are researched. Attendees will receive an understanding of challenge of analyzing firmware and backlash patterns for memory corruption.
Much for having me today. Hello. We'll try that again. I'm excited to be here today, and I'm going to be speaking about a theme, hacking 20 devices in 45 seconds. But that's just meant to be a flashy term, and we'll do it, don't worry. But it's really about how do we automate bug hunting in IoT devices, both to make our lives easier as attackers and defenders. Today we're going to talk through the fundamentals of program analysis as it applies for vulnerability discovery. I'll give a little background on past work in the field, motivate why we want to use automation instead of drinking a lot of energy drinks and sitting around for 12 hours a day, talk about some of the road bumps, some of the challenges in automating analysis, and talk about why that's different in IoT systems from other systems. Then we'll go through how we've done some work to improve the publicly available tools in this space. And then actually, let's do the 20 devices in 45 seconds. Then we'll apply the tooling to find some bugs. We'll go through those and talk through them. So as background for myself, I'm a low-level hardware and firmware reverse engineer. My focus for a long time was on 802.15.4 and Zigbee systems. I maintain some of the open source frameworks that people use to assess those, so don't send me any bug tickets here. We'll all be drinking tonight, but later. I've had the pleasure of speaking at a number of conferences, but I'm super excited to be here. This has been one of the most fun conferences so far, and unless you guys throw a lot of tomatoes at me, it will continue to be a fun conference. I am the CEO, and feel free to throw. I can dodge. What? No comprendo español? Sorry. So I'm the CEO and the lead of firmware analysis at a company called Pilot Security. We do automated firmware analysis to find bugs in these types of devices. And I'm also privileged to be one of the partners at Riverloop Security, where we do consulting services along these lines. Sophia, Sophia, who's not able to be physically here today, she apologizes, is my co-author on this presentation and did a lot of the work for it, so credit to her. Her thesis was in exploiting CPU side channels back before we knew that Spectre and Meltdown were big things. And she leads our automated analysis at Pilot Security. So today, let's talk through and sort of put this in context. In these type of embedded devices, there's the hardware, the physical plastic casing that looks nice and shiny, the circuit boards and all of that. And then there's the firmware, whether that's the code that the vendor wrote, or libraries that they got, or any other code that's gluing together the actual logic there. And then last but not least, often, there's a back end, right? These are Internet of Things devices after the fact. They are connected to something. Maybe that's providing a user interface, driving a mobile app, etc. But today we're going to be focusing on the firmware. So how do people deal with this today? And many of you know these and know many more approaches than we have time to go through. So first of all, one approach is to network scan the device. Treat it like a network asset. We're going to nmap it. We're going to start going through the services that are listening. Well, although when you Google for network pen testing and find stock art, they apparently think that all you have to do is put a laptop on top of a box of donuts. It's much more complicated than that, right? Especially on embedded, we're often hampered by unstable network services that fall over when we scan them. And then we're also limited at just looking at the exposed network services. We miss all of these other important attack vectors, including a lot of these devices call out to their servers instead of in, right? By the time you take an IoT device and put it inside an airplane fuselage, it's no longer something that has all of its ports available for you to easily assess. Another approach is doing manual firmware analysis. There's great open source tools, I'm sure many of you have used them, things like binwalk, that can help you extract out of a firmware image a file system. And then we'll go through those and look for outdated versions, hard-coded passwords, all the stuff that you find, and probably pick out some binaries as well to reverse engineer. But as some of you may have found out or deal with on a daily basis for some of us, right, this can quickly become a lot more complex. Somebody changed the file system binary format a little bit. There's a lot of important items outside the file system that you need to look at in the kernel and the bootloader. And then outdated libraries are often statically compiled in, and it's not going to just stick out like a sore thumb, right? So there's a lot of struggles here, but it's still an important tool. And lastly, we could physically probe the device, right? Get out the soldering iron, maybe use some open source tools, JTAG and Noom, things to find serial ports, maybe listen to the radio frequencies, interact with those. But number one, obviously we need physical devices, right? As you saw some of the talks yesterday and earlier today we're using. This is the basic low-cost tools, the things that you may deal with, good fed, app emote, yardstick. They're great for what they were made to do, but quickly, somewhat different devices or security on the devices can pose to sort of break those hacker tools. And we can only test, again, some avenues, right? These exposed debug ports. So today we're not going to be talking about any of those, right? We're going to be talking about how do we use program analysis to help us go through the firmware. So, first of all, to give some foundations here, I want to talk about bug class patterns. The good news is firmware on IoT devices has the problem of the early 2000s, right? These do not have the modern exploit mitigations that Adrian talked about. There's no, they're full of stack buffer overflows. We'll get to plenty of those later. Constant size buffers, unchecked boundaries. Basically, we should be happy if we're wearing a black hat, right? There's limitless possibilities. Some things we may look for are indicators like stir copy, mem copy, things that could be used in a vulnerable way. But those alone are not enough to be an issue, right? Those could be used totally safely, copying a constant. And then, of course, we have coming in externally provided input, and whether or not it has bounds checking is another indicator. So, the objective of taking bug class patterns into program analysis is to encode these in a way. Encode our knowledge as reverse engineers and vulnerability researchers into something that the computer can do for us. So, all of those bugs that we talked about, right, are really, I would argue, two operations. They're reads and they're writes. And if we deconstruct these bugs, if we take them down to a level of abstraction, we can then express them in terms of reads and writes put together. And if we do that successfully, which is not always easy, we can express these vulnerable properties of a program in an intermediate language. So we can fully embrace the weirdness of these bugs. So let's take a look at an example here, right? We have, your intro to hacking main function where we have a constant size buffer, right, that's been allocated on the stack. We're going to read in some pleasantly unbounded user input, and we're going to write that to the stack using, in this case, stir copy. Now, for the sake of doing this at scale, one thing that most people doing program analysis do is they abstract away the details inside, libc functions like stir copy, so that we don't have to dig through all of that assembly code. And by the time we've gotten to step 3, we've written the input to the stack, we get our buffer overflow, and this is the type of thing that we want to find automatically at scale, especially when it's this simple. So let's define briefly what sources and sinks are. First of all, a source is where external input comes into the program. What is this operation that we know we can control or an attacker can control, like receiving network data, right? This is the receive function, the read function, whatever it is. And this is important because it helps us filter out unreachable bugs. Secondly, the definition of a sink is where does the external input get processed or written to memory? Where does that write happen? In this case, we're going to use these to also filter out unreachable vulnerabilities. So, before we go any further, there's some great past work that I would not be doing it justice to skip over. So first of all, from those of you who saw the title of the talk, it is deliberately a play on this talk from DEF CON 22 that a lot of our friends gave, called Hack All the Things, 20 Devices in 45 Minutes. And they, like I, have a counter counting down from 45 minutes, but I'm not going to, neither talk took only 45 minutes to find all the bugs. What I was going for today is showing you how we can automate a lot of this work. So instead of weeks or months of analysis, how can we show how the computer can do the heavy work for us and run very quickly? There's also a number of good resources on program analysis for those of you who want to follow up and read more about this. These are some references that you may find interesting. Everything from Rolf-Royce's Recon talk to a number that Sophia have given, to if you want to pour through a master's thesis, Sean Heelan's thesis has some great material on this. And then there's, of course, a lot of tools like we've probably all used, right? On the left-hand side, source code analysis tools. Anything from a source code analyzer to things that can do fuzzing based on source code. Maybe things like LLVM compilers that I'll talk more about in a second that can look for bugs. And then on the right, binary analysis tooling, whether that's dynamic or static. So there are a lot of tools out there, and let's drill in a little bit first to how compilers work as program analysis tools. First of all, LLVM lifting via Clang is great. And from the developer side, if any of us are running product security programs, we probably should be looking at how can we get our teams to use this, right? If you start compiling through Clang, there's a lot of built-in security checks that can run on the intermediate representation to find a lot of things. However, it's a compiler. As reverse engineers who just have the binaries, we need a lifter. So it's maybe not the best tool for looking at binaries. Some tools like Mixema have worked to lift from compiled binaries into this intermediate representation. But unfortunately, this often produces a massive output. You may not get all the benefit, right? Again, it's a compiler. It expects to have rich type information that we don't have when we're coming from the assembly code. So using tools like Binary Ninja can help lift from assembly to an intermediate representation similar but different from LLVM. When we work on this intermediate language, and sometimes you'll hear me talk about it as MLIL, or medium level intermediate language in this talk, we can run our analysis there. There's also a number of other tools, IDA, Ghidra. They have different limitations from the price to the UI to where they're made to, the Ghidra, for example, doesn't have a native single static assignment form, which can be really helpful for program analysis. So, why automation? Well, we all enjoy keeping our jobs, and probably many of us by billing by the hour. However, that won't scale, right? So we have some source code analysis tools today. They're good at finding issues, maybe like command injection. But it's tougher, especially in embedded devices, to find two other important types of issues. First of all, when a binary library that somebody has compiled in introduces the issues. Think of a hardware abstraction layer or library that's given to you by a chip vendor. You're going to go ahead and compile this in. You may not have the source code, but you still want to analyze it to see what types of issues it may introduce. Likewise, there's a lot of issues that may get introduced during compilation. Right? The classic example here is memset. You're clearing out your crypto buffer, you're zeroizing that out, and the compiler says, hey, you don't need that, right? Why bother? And so this is something that we can see when we analyze the binary, but doesn't show up well in a source code analysis. Lastly, and I'd love to see a show of hands here, how many people have heard from their development teams, if you work at a product security company or work doing product security at a company, hey, your source code analysis gives me so many false positives. I hate it. I never want to see it again. This isn't even code that's in the product. Anyone? Anyone heard that? Wait, developers only complain in the US? Come on. Okay, thank you. So, things that get compiled out due to pound defines are things that, again, we can target the analysis we're looking at when we look in the binary form. So this is the classic slide that a marketing person put up, right? It's a scary number. There's a lot of devices out there, and there's not enough of us. But joking aside, right, if you have 15 billion devices coming online between now and 2022, and allegedly 1.8 million cybersecurity positions unfilled, and the numbers on this vary from like none to 4 million, depending on who you ask. This is, one of the reasons why I'm passionate about finding ways to automate. Also, because I'm lazy. So what is this automation trying to do, right? It's trying to find issues before they can cause harm. Even if all of us were busy 24 hours a day, and we had enough people to audit every IoT or embedded product or every project in general before it went out, there's still some issues. First of all, the cost of fixing the bugs we find is demonstrably much higher when it's closer to the release, right? When it's farther from when the bug was introduced, it's more expensive, takes longer, is more things have to get changed to fix it. And lastly, if we can find it earlier, there's a lot higher likelihood that more percentage of the bugs are going to get fixed before we ship it to our customers. So how can we push finding it left of ship? One example is things like GitHub does internally now, right? Where they're saying, hey, you have some Node.js code. We're pretty good at knowing when somebody reports a vulnerability. We're going to send you an email telling you of vulnerable code. That is great for some ecosystems with well-defined package management that can be scanned for. And that's the type of thing we're trying to find and apply to more types of ecosystems, specifically embedded, where if we had a package manager for embedded, if Yocto was well used, we'd all be a lot happier. The second thing is that we need to have thoroughness in large code bases. Myself, and I'd argue probably most of us, as human researchers aren't perfect. If we get a control flow graph that looks like that, frankly, good luck, right? Good luck thinking that we're going to be sharp enough, well-rested enough, and have the patience, frankly, to check every potentially vulnerable code path in that function. And that's a real one. So we need to make sure the check's good. So in program analysis, we're trying to encode an expert researcher's methods so that the computer can run this in multiple iterations. I jokingly put on things about Monster energy drinks because this is how Sophia finds bugs. And she's not here to defend herself for this methodology. For her own health, we need to have program analysis techniques. But let's see what some of the challenges are, right? It's not all just the promised land. So, first of all, the question is, can we apply techniques that we've used in traditional computation to solve these issues in embedded? And the answers definitely vary. First of all, in traditional computation, and I use that as a general word for web apps, kernels, etc., there's been a growing adoption of type-safe languages or language extensions that can reduce basic memory errors. In embedded, we have yet to adopt things like well-tested techniques that Microsoft adopted in the early 2000s to ban unsafe function calls. Likewise, in traditional computation, there's well-optimized tools for static analysis. But in embedded, it's been lagging behind. In some reasons, at least some of the reason, has been due to a lack of good processor support for the variations of architectures that we have. But now tools like Binary Ninja and Ghidra are really helping catch that up. In traditional computation, you might give your developers source code analysis tools. Some of them may integrate into their development environments and highlight the bug right as they type the code. But in embedded firmware, not only is there widely divergent development environments, because every single microcontroller company gives you a different IDE, but also there's a lot higher frequency, I would argue, of taking in binary libraries. And lastly, in traditional computation, we have well-used automated fuzzing suites, whether it's the big companies or whether it's things that people apply individually, all have harnesses or often have harnesses that are fuzzing for security vulnerabilities. But in embedded, this is tougher, right? We have hardware interrupt handlers, we have custom chipsets and board layouts that require instrumentation. This raises the barrier to entry. So to answer our question, yes, we can apply these things, but it's non-trivial to implement. We can't just port or use the existing tools. But we can apply techniques. We can take static analysis to screen for bug classes, like we'll be showing today. We can use emulation or partial emulation to drive and support some fuzzing. We can use techniques like satisfiability solving to figure out some cases in the control flow. And importantly, we should be integrating into the development cycle, right? So just like a shop is, using continuous integration to build it, send it to QA, and get it back, so too, if we automate it, instead of having us on the receiving end, I can't turn around in 10 minutes and give you results, or in 45 seconds. But an automated program analysis can give some of that feedback in the build process right to the developer, hopefully meaning they actually implement it and ship more secure code. So the reason I've been focusing on and researching this, frankly, for the past few years is because my objectives are let the computer find the majority of issues, let us focus on the more interesting things, and overall, let's help our customers by catching issues before they cause harm. But another challenge is determining bug efficacy. And I'm going to go through 3 specific technical areas where this rears an ugly head. First of all, how do we encode these read and write primitives, right? I said you can just simplify them to read and write primitives. Well, now I'm here to tell you it's not that simple. For example, in some of the vulnerabilities that I'll cover in a moment, Tenda, a router manufacturer, has this call do system command. It's a dynamically linked library that they bring in that basically calls system vulnerably under the hood. But because this is across a dynamically linked library into a different program that you're analyzing, stuff like this can add complexity to encoding the sinks that we talked about. Likewise, information flow analysis. I'll dive more into this in an example in a second. But this is basically making sure, how do we know that the variable one function is touching? How does the computer realize that's the same one that's being used in a different context? And lastly, variable range recovery. This is important because, for example, if something does a length check, and then it's used in a way that would only be vulnerable if the length was over a certain boundary, we need to understand that. The computer needs to understand that in the program analysis. One way to do this is to do symbolic execution on everything. That is unlikely to work, and it certainly won't work in 45 seconds. So let's look at an example of where we have to do a range recovery. If we take that same vulnerable program from earlier, and now we add the code in blue, right? So still maybe not the best written code, but let's go with it. We are now checking that the input is, if it's over 100 bytes, we're going to error out, and we won't do the vulnerable copy into the buffer. So we have this base assumption that stir copy does a memory write. The write length is the length of the source buffer to stir copy. But now we've added this check in blue, and now we need to understand a few more things in our program analysis. First of all, we need to know the size of the destination buffer. And secondly, we need to know what we've bounded the length of the source buffer, in this case input to. Now, the exact techniques for this would be a whole talk in its own right, and so I'm not going to dive into it here. But I do want to raise it as something that we have to overcome when doing this. So now let's talk about 2 issues that we ran into when preparing for this presentation, and how we're going about fixing them and making that so others don't run into it as well. So the first, for those of you who have done reverse engineering on MIPS binaries, you probably know that they lead to their own challenges. In this case, Binary Ninja was not able to find the main function, and when it couldn't find that, it really didn't find any other functions, so nothing had any vulnerabilities. Well, that was a red flag, because they obviously had vulnerabilities. So what we wanted to do here was figure out what was going on. And our technique for this was saying, yes, it's MIPS, because this is where the issue is happening. We're going to find this mulibc, this function, the entry point. We're going to extract the first argument and dereference it, and then grab those 4 bytes. Then we'll do a sanity check to see, okay, this is a function preamble. We'll set that as a function, and then reanalyze the whole thing, which is expensive. Luckily, the Binary Ninja team's great, and after we found and gave them this patch, they've now put it in. So if you're on a recent version, you should not run into this issue. If so, blame them. Another is going back to that topic I talked about earlier with memory references. This is an example of how we have an issue understanding what goes into system, right? So in this case, system is the vulnerable sink, and we want to understand if the attacker can control data going into it. Well, what's happening here is a variable is being assigned based on a stack address reference. Then data gets copied into it, in this case through sprintf. And then that same stack address reference is used to set a different variable, which is what's passed into system. Right? As humans, we look at this, and all of you are nodding and being like, yeah, I don't know why the computer can't follow this. This clearly is the same thing. It's being set by constants, not an issue. But this is very difficult to generically trace from a program analysis standpoint. Okay. We've gotten through the background of program analysis. I'm sorry that not everyone is coding it up at this point, but I'd be happy to talk with anyone afterwards who's interested in diving more into that. But now let's go through some examples, right? I have a thing against live demos, so I have taken the liberty of having the 45 seconds elapse earlier today and then taking screenshots and putting them in here. Because me zooming around my computer screen while standing behind a desk is certainly less fun than me standing up here where I'm within range of your tomatoes. So let's go through some examples. We're going to go through 20 devices. We picked these by looking at various lists of what were popular devices in different markets. And then, to be honest with you, the toughest thing, because I was invited to give this talk. Oh shit, you don't want to see that. Sorry. Well, that's fun, huh? Loading. Who hit the internet on me? Okay, sorry about that. So, talking through these devices, one of the toughest part was, I was asked to give this talk about 2 months ago. We give people 3 months notice before releasing new bugs on stage against their targets. So the toughest thing was finding a majority of devices that we could find automatically, and then figuring out if somebody had manually found those in the past, so that I did not feel bad or get yelled at for releasing them here. Now, the last 4 don't fall into that group, so that's fine. We'll just leave out the exact memory addresses, and no one will figure it out. So, first of all, to start off, this is a Tenda router, and we're going to go pretty fast through this, right? So we're going to look at this one on how the HTTP requests are processed. And the great thing is I figured we'll start with this one because it has an awesome feature. In its product literature, it has anti-hacking. And I thought, well, that definitely means we're not going to find anything automatically. So here's what we found automatically. Web requests came through and get processed first by this HTTPD, right? It's going to read the user's data from the socket, and then it passes it off to app data center, which parses and uses the data. Well, the first thing that I saw popping up was this, right? A vulnerable system call. Let's dive into what that is. Don't worry, somebody was reported, but unpatched. It was actually reported on a different device from this vendor, but through program analysis, we were able to quickly see that it was also available on this model of device. And what it actually is that inside their handling for USB ejection, which obviously has to be available over the web, it copies in some data in an unbounded form, unsanitizes, puts it in, calls system on it. Great. Typical command injection. Hint, none of these are going to be thrilling, right? What's interesting is that we can find them automatically. Okay, on the next device, on Tenda's AC5 device, again, similar binaries. One looks a little different. This case as a format string vulnerability. What this actually is that it's reading in a parameter from the HTTP web request, and it's using this as the format string. So you could do %n or %p, your typical format string types of attacks to control the stack. Okay, let's go appreciate some stack buffer overflows. We'll stay on Tenda to start. In this device, it's their AC18 device. And at this memory address, and don't worry, the only one I'm disclosing is the one I've highlighted. And this is the one that, again, has been disclosed previously. They're reading in the SSID field that somebody set through a web form and does a stir copy into a fixed size buffer of hex 40 off of that. This can be triggered via this very complex exploit that you see here. Yup. So on AC15, another one from this family of quality devices, another stir copy. What this comes out to be is this time they read in this idea of where they should bind their MAC address to some IP. Now what's interesting here is think back to this grid that I showed you earlier, that control flow graph of so many devices or so many points in a program. If somebody manually finds an exploit, they're likely to find it in one place. You don't need a second one. Even if you report it to the vendor, it's incumbent, I think most would argue, on the vendor to find all the places this same exploit technique hits. And in this case, basically any field that you can submit to this web application has a stir copy buffer overflow. So program analysis is patient enough to find all of them for you. And again, can be triggered via a slightly more complex vulnerability. This time you need to provide 2 arguments. Finding another one, this time in device number 5, AC9, it's the NTP server field on this device that is vulnerable. So, okay, let's give that a break. Let's go look at some more command injections. We'll stay on them for a little while longer. Remember how I said earlier some of the issues are trying to find a sync on a device when it's linked in? This is that one, right? Where do system command is where the vulnerable function is. In this case, let's see what's going on. They're taking in a MAC address, passing it down. This can be attacked. Sophia wrote up a really complex proof of concept here where you have to add a semicolon before you run your command. Looking at AC7 now, let's see what we have here. We have another command injection through another function where the device name is vulnerable. Are we getting the feeling here that Tenda may not be what I install in my house? Okay. Let's give them a break. Let's go look at some other vendors, because this is certainly not limited to one. Let's look at some more command injections. In this case, in a D-Link modem, router in this case, it has this BOA constrictor, or whatever, binary, that has system called at this address. In this case, it's reading in a command and kindly processing it for you directly into system through sprintf. The nice thing is it logs out what you did. Now, a bonus is that I want to throw in, right? Everything we're talking about is program analysis, but I don't want to give the impression that the only thing we can find automatically is things like stir copies or command injections. Another example of things that we don't want to look for as humans, at least I don't, are things like hard-coded passwords, right? Where, running grep or looking at etc password on every device you assess gets boring. Remembering exactly which one's MD5 and not in the encoding is annoying. So additional things we can find on that device. Okay, let's go back to command injections. On the D-Link DIR 816, they use their go-ahead, which is an open source web server, open source and commercially available web server. And in this case, it takes in a command through an ASP handler and passes it down again to system. Why not? Let's look at Huawei, known for some of the most secure devices available on the market today. Their UPnP binary, Universal Plug and Play, or the network service that's there, calling down into system at this address. In this case, they decode some user-provided input from an XML node and pass it right down to system. Again, this was found manually in 2017, but most of the work in finding these is not finding them, it's figuring out if somebody else had previously found them, given, as I'm sure you all know, CVE entries are really well written. ASYS has an HTTPD server as well that we get a hit on through the automated analysis that system is being called at this address. And if we look at what that is, it's taking in an email form through something and passing it down to system. In this case, you can't use a semicolon, you have to use a pipe character, so very advanced exploitation. Ubiquity makes a product, and I include this one here just to show that it's not always system, right? We need to be aware of all of the different sinks. In this case, exec-l, that's again a vulnerable function. Okay, let's take a look now at some stack buffer overflows. I've worn you all out on command injections. Let's hit another TP-link device. In this case, again, they have a web server. It calls stir copy. The data coming into that came from how they take in an IP address through a web form. This was found manually earlier this year and reported. In an ASYS device, let's hit a few of those. Again, stir copy. In this case, takes through a CGI binary that takes the username, passes it right down, copies it into an unbounded buffer. Another ASYS device, slightly different HTTP binary. In this case, they do the buffer overflow not through stir copy, but through sprintf, right? Because this can also copy off the edge of a statically allocated stack buffer. Okay, let's look at a few, I think just a few more examples. Let's look at an example of a controlled format string like we touched on at first with Tenda, this time in TP-Link. This is an R600 VPN device, and we can just see that this vfprintf call here is a format string, in this case that the attacker can control through, I forget exactly here, I think it's another email address field that is used like a format string. Okay. Now for the ones that I will purposefully omit the actual memory addresses from, I'll just tell you the binaries. So LawView IP camera has a binary called exec system command. One might think this is where you might look for a command injection. You are correct. We disclosed this earlier this month, still haven't gotten a response back from the vendor. We'll continue to follow up. On another, I believe this is another camera. If you're going to have hard-coded passwords, which I'd argue you should not do, you definitely should at least salt them. And in this case, we see that the automated analysis can call it out because there's no salt being used. We're going to finish disclosing that one. On this commercial DVR used to record security cameras, there was a blog post that was never formally reported in 2013. They released a patch in summer of 2018 that specifically says in the release notes that it's there to mitigate a large number of security vulnerabilities. Yeah, no. Still have not heard back from them on those technical details that we sent over. On Linksys camera, the file.cgi handler was previously reported to be reachable and allow for file access, but automated analysis also quickly was able to flag that it had command injection as well. So I've gone through those in rapid succession. I'd be happy to talk to anyone about more details about how one of those is found, the actual math behind the processing, or any other topic you want. Thank you so much for having me. It's been a great time to be at this conference, and thank you for being so welcoming and putting up with my absolutely terrible Spanish. I will work on it, I promise, for next year. I'm happy to take any questions. It looks like we have a few minutes remaining, or let you get on to closing and closing ceremonies. Thanks. Hi. Thanks. Somebody's not letting me off that easily.
Hey, Ryan. Thank you for being here. It's kind of clear that what you're using for things, like you're doing different functions, but what are you doing to find the source? Are you like doing manual audit to find like the different potential source for your data flow analysis? Yeah,
in this case, in the examples we showed today, we're not pegging on specific sources, but instead recovering control flow back up from the sink and seeing if we are able to concretize the parameters to the sink. And if we're not able to concretize them, we don't know that they came from something that is safe, then we'll flag it for a human to look at. But absolutely, to your point, in some other tooling, I didn't show it today, we also look for specific sources. And in fact, how we pick which binaries to look at out of the whole file system, right? These have hundreds of binaries. You want to know a few things. Which ones are actually being run? And we do a lot of analysis to figure that out. But also, which of those then bind on a network interface, so that you pick ones that are more likely to have attacker-controlled input.
Hey, what's up? Have you ever considered to take a look into ICS devices?
Yeah, absolutely. Yeah, and on those that are embedded Linux focused, this works well as well.
Okay, cool. Thank you.
Yeah. Okay, thanks very much, guys. Have a great rest of the day.